Okay, hello to everybody, and here we are with the next lecture again on limits, and in particular on theorems on limits. So I start here by giving you this title and theorems on limits. Second part. So we talked about the algebra of limits, and in particular we treated the cases of sum, product by a constant, and ratio, and so on. And now we go to another important operation with function, which is the composition. So I recall you what is the composition of function. So we are given two functions. So this is the definition. We have a function f. So we have E and F, two subsets of R, and we have a function f from E to R that has the following feature. The image of E, of the domain, the image of f, is a subset of capital F. And then we have another function, G, again from F to R. So the picture we could bear in mind is the following. There is a set E here, another set F here, and here there is a set of reals. So we have a function f moving from E to F, a function g moving from F to R, and so we can compose these two functions, obtaining a unique function f from the composition of G and F, going directly from E to the reals, and the result of applying G composed F is exactly equal to the result of applying first F and then G. So the definition is quite simple. So the function G, and there is this little o f, this small ball, I don't know how to call it properly, goes from E to R and associates to every x G evaluated in f of x. Okay, this is the definition, and this is called the composition of the two functions f and g. Now, the theorem is about the limit of composition of function. And says the following. You consider a point x bar in DE, so an accumulation point of the reals, and of the set E, and then limit for x going to x bar of f of x is L, and L is an accumulation point for the image of f, and since the image of f is a subset of capital F, this is also an accumulation point for f. Second, since it is an accumulation point, we are authorized to take the limit of g of y for y that goes to L, and we discover that this is equal to k. Then we compose these two limits, and we have that the limit for x going to x bar of g composed f of x is equal to k. We can organize a proof in several ways. And probably the shortest proof is a proof made by sequences again. So here we have proof, and we say let xn be an arbitrary sequence that fulfills the following features. The whole sequence xn is contained in E minus x bar, with xn going to x bar, and so that ffxn is in f minus L. So you can wonder whether it is possible. It is possible to take a sequence, a sequence that is never x bar, but that tends at x bar is possible because x bar is an accumulation point of it. This is what we already studied. But moreover, we add that the sequence of the images never goes to L. Is it possible? And the answer is yes. It is possible to find such a sequence, so such a sequence exists. Since on one side x bar is in DE, and on the other side L is in D, is an accumulation point of the image of F. So think of it, try to prove, okay? Think of this point if you are not convinced. I prefer to go straight with the proof. And so here we use the theorem of limit through sequences again. And the first part, the easy part, okay? Since the limit of the function exists, the limit of the sequence of the images of the element of the originary sequence exists. So we have that if we take xn and we apply f, so we obtain a sequence yn that tends to L. Okay? So this means that if we take G composed F of xn, this is equal of G of f xn. This is G of yn. But we know that G of y goes to k as y goes to L, and here yn goes to L. Moreover, yn is in f minus L. So again, we apply the theorem of limit through sequences, again the first part, and so we have k. But now what we proved is that for an arbitrary sequence xn that goes to x bar, always remaining in the domain of the function and then of the composed function, and never going exactly to the basis point x bar, the limit for x going to x bar is equal to k. So now we apply LTS2. Remember that LTS2 requires the arbitrary character of the sequence we are using. So by LTS2, we have that G composed f of k tends to k for x going to x bar. Okay, this is a sort of shorthand writing, and it is just a notation, just another notation. I take advantage of here to introduce it. Another notation for the more used and more popular limit for x going to x bar of g composed f of x is equal to k. It is exactly the same. So why is this theorem important? This is the remark I want to offer you here. This theorem is important because this theorem allows us for the procedure, which is well known and well loved by students, the procedure called change of variable, which is very useful in computing limit. And so let me explain it by an example. I know you already had examples in exercise, so perhaps it is not so useful. However, sometimes it is better to have many examples than few examples. So let me give you this example. Compute the following limit. The limit for x going to 0 of 1 minus cosine of x divided by x squared. This is an important limit, okay? You probably already know that. And the first thing is to observe that by using the usual formulas of, I don't know, duplication of angles, I don't know, they have strange names. However, 1 minus cosine of x is equal to 2 times sine of x squared, x divided by 2 squared. Then let us go to the limit we are interested in. It is 1 minus cosine of x divided by x squared is equal to 2 sine x divided by 2 squared. And here we have x squared, but let me divide by 2. So this means that here we added a denominator 4, and let us compensate it with that. So 2 over 4 is just 1/2. So here in the final passage, I write down 1/2. Then we have sine of x over 2 divided x over 2 squared. So here we have another factor, sine of x over 2 divided by x over 2. Okay? So this is a very easy point, but just let me read this limit. read this limit as a composition of limits. So let me introduce two functions. A first function, which is f of x, which is x divided by 2, and g of y equal to sine y divided y. Okay? So again, G composed f is equal to, of x, of course, is equal to G of f of x, by definition G of x over 2. Therefore, instead of y, here we have sine x over 2 divided by x over 2. Okay. Now here we have that the limit for x going to 0 of f of x is equal to the limit of x going to 0 of x over 2, which is obviously equal to 0. So by the composition theorem, you have that the limit for x going to 0 of G composed f of x is equal to the limit for y going to 0 of G of y, which is equal to the limit for y going to 0 of sine of y divided by y. And we already studied that this is equal to 1. So here, let us go back to the previous writing of this limit. Here we have 1/2. Here we have a factor that goes to 1, and another factor that goes to 1. So the overall result is that by the algebra of limit that says that the product of three limits is equal to the limit of the product of the three factors. So this is 1, 1, 1/2. So this tends to 1/2. Okay. And so this is a very, very easy task at this level. And this is a sort of pedantic application of this theorem, but you already know that this theorem is very important, is very well used, because it allows you to do this operation of change of variable. So, in other words, in practice, one can compute a limit by the well-known, the usual change of variable procedure. So let us be more rapid here. If here we are to compute the limit for x going to 0 of 1 minus cosine of x divided by 2. So this is the limit of x going to 0 of 2 times sine of x squared divided x half divided x squared x. Okay. Then we introduce the new variable y is equal to x over 2, and we know that if x goes to 0, then also y goes to 0. So the given limit can be rewritten, can be rephrased as limit for y going to 0 of 2 sine of y divided by y to the second power. Oh, sorry, here there was a 4. There is a 4 here, and this is equal to 1/2. So this is a message is learn how to do change of variable, but the other message is remember this important limit. The limit for x going to 0 of 1 minus cosine of x divided by x squared is equal to 1/2. Extremely important. Okay. And then we can also compute another important limit, another example which is very important. That says the following: compute the limit for x going to minus infinity of 1 plus 1 over x to the power x. Of course, this is an important limit of the E-type. Is one of the huge family of limits that can be reconducted to the limit that defines the number E, Nepper's number. And again, we perform a change of variable which is y is equal to minus x. And so minus x go to plus infinity, since y goes to minus infinity. So the limit becomes the limit for y going to plus infinity, like in the limit that defines E, but here we have 1 plus 1 over minus y to the power minus y here. So we have that this is equal to the limit for y going to plus infinity, 1 minus 1 over y to the power minus y, which amounts to the same limit for y going to plus infinity. And here we have 1 over 1 minus 1 over y to y. And here we write it as a limit for y going to plus infinity of y divided y minus 1 to y. Let me write it as the limit y going to plus infinity to y minus 1 plus 1 divided by y minus 1 to the power y. This is equal to the limit y going to plus infinity of 1 plus 1 over y minus 1 to the power y. And again, another passage, which is the limit for y going to plus infinity of 1 plus 1 over y minus 1 to the same power here, y minus 1. We are trying to reconstruct the original limit that gives you E, and here we add another factor, 1 plus 1 over y minus 1. Now we can change the variable and introduce zeta is equal to y minus 1, and of course zeta goes to plus infinity since y goes to plus infinity, and here we have lim zeta going to plus infinity, 1 plus 1 over z to the power z, here 1 plus 1 over z, and here notice that this guy here is exactly the limit that defines E, that defines the number E. So here this goes to E, and this other guy here goes to 1. So the result of this limit is equal to E. Very, very simply. Okay, and with that I say, here we finish our introduction on composition of function, and you have to be trained on that and to compute a lot of limits, but okay, we will see many limits also together. And so there is, before going to the next topics, I want to stress another factor, and this is a small chapter, which is how to prove that a limit does not exist So we will see many methods, and the first, most general, is to use LTS in a negative fashion, so by exhibiting two sequences going both to X bar, but whose sequences of images have different limits. So, and the typical example is lim, very stupid, but lim for x going to plus infinity of sine of x. And consider two sequences, xn, an, let me call it an, is equal to n pi, and we have that sine of an is equal to the sine of n pi, that is always 0, that converges to 0. Consider also bn, which is 4n plus 1 pi over 2, namely 2n pi plus pi halves. So the sine of bn is equal to the sine of 2n pi plus pi halves, but you know that 2n pi just means that you take n complete circles on the circle that defines the trigonometric functions. So this is equal to sine of p over 2, and this is always equal to 1 and converges to 1. And now, be careful of the logic here. Look at here we have these two sequences, both go to plus infinity. But then we consider the images of the sequences, and they go to different places. The first one goes to 0, the second one goes to 1. And by LTS theorem, we know that this is incompatible with the existence of a limit. So, therefore, the limit for x going to plus infinity of sine of x does not exist. Indeed, if it existed, then every sequence sine of xn with xn going to plus infinity would inherit the same limit. So, such sequences would have the same limit always. But this is not the case. We just proved by direct exhibition that this is not the case. Okay? So, this is a sort of negative use of LTS theorem. First part. Negative in the sense that it is shown not to compute a limit, not to find a limit of a subsequence or also of a function, but to show that a certain limit does not exist. There is another example which is very important, which is the following, and says the following thing: consider the limit for x going to 0 of sine of 1 over x. Okay? So, first of all, you can reason by change of variable. But you should distinguish x larger than 0 from x smaller than 0. It becomes complicated now. At the end of this lecture, it will not be complicated. Otherwise, because of course, the idea is that here you define y is equal 1 over x, that goes to plus infinity, and then you fall on previous example. But to fix everything now, since we still don't have right and left limit, we will have it with the next video, it becomes quite complicated. The second strategy is, again, on the other hand, we define two sequences an is equal to 1 over n pi. So we have that sine of 1 over an is equal to sine of n pi, which is equal to 0, that goes to 0. Of course, 1 over n pi goes to 0. But again, inspired by the previous example, we have that bn is equal to 1 over 4n plus 1 p over 2. So we have that the sine of bn is equal to 1, which goes to 1. And this goes to 0 too. So again, the limit for x going to 0 of sine 1 over x does not exist. For this function, it can be useful to have a sort of pictorial idea of what happens. You have the function is an even function, so from here, sorry, I changed color, it is better. From here and here, it is a nice function, and it is equal, and then it starts like that. The picture becomes quite neurotic, especially around 0, So, and the idea is that at every neighborhood, even a very small neighborhood of 0, the function oscillates, and it oscillates infinitely many times, from -1 to +1. Okay, infinitely many times. This is a very neurotic but quite spectacular behavior. And this is why you can exhibit sequences that goes to 0 but whose images are 1, or whose images are -1, other images are 0. And also you can also choose other images between -1 and 1. Okay, think a bit of it. Another example which is related to this, but the final result is very different, is the following. Consider the limit for x going to 0 of x sine of 1 over x. Let me start from the picture here, which is very different. The picture here is the following. So let me draw these two lines, y is equal to x. And here y is equal to -x. And start from this basic observation that -1 is not larger than sine of 1 over x, which is not larger than 1. Then multiply by x for x larger or equal 0, and here you have -x less x sine of x, sine 1 over x, less or equal x. And for x less than 0, we have that x less or equal x, x sine 1 of x less or equal -x. In any case, what happens is, in both cases, we can apply double comparison theorem, and the left side we go to 0, and then in right side goes to 0, then by double comparison theorem everything goes to 0. And the picture here is quite well explanatory, because here you have to stretch a sine graph in this way, but you see that at the end you go to 0. And so, notice that here we had to separate the behavior in the left hand side and in the right hand side case. Good. And so in the next lecture we will make this procedure rigorous, separate what happens at the left and what happens at the right. Okay, let us go for the next video.